Okay, I think we can get started. So good morning, everybody. Thank you so much for coming. This is ML Hat 2020. This is the first KDD workshop on deployable machine learning for security defense. So my name is Gang Wang. I'm an assistant professor at University of Illinois. So very excited to be co-organizing this workshop with two amazing colleagues, Ali and Ray from Blue Hexagon. It has been really fun working with them in the last few months. So the initial thinking behind this workshop is that we were hoping to get together people from both industry and academia who are interested in machine learning and security to really think about what are the challenges that are there to deploy machine learning methods to solve practical security problems. So also think about the limitations and the security issues within the machine learning models themselves. Hopefully through today's workshop and discussions, we were able to identify new directions and new ideas to address those issues. So today we have a really packed schedule of keynote talks, technical discussions of 8 amazing papers, and also a panel discussion. So before we get started, I wanted to thank all the TPC members who have been working really hard to make this workshop happen. Hopefully some of them are joining us in today's discussion as well. Also wanted to thank our authors for submitting their works and also preparing the talk videos within a short notice. Also thank our keynote speaker, David, our panelists, Cormac, Sadia, and Sean for joining us for the discussion today. So without further ado, so let's start with the first session where Ali will be moderator. So Ali, you can take over. Oh, Ali, we probably can't hear you.
Thank you again. Thank you very much.
Okay,
so hi, everybody. I am Ali Ahmadzadeh. I am the head of AI and threat research at Blue Hexagon. And I'm very happy to have this workshop with two amazing friends. Gang mentioned, Ari and Gang. This has been a very fun experience for us. So without further ado, I'm introducing David, our keynote speaker, David Wagner. Well, he's a professor at the University of California, Berkeley, very well-known researcher in cryptography and computer security. And he has some amazing work on cellular network, wireless communication security, and recently he's working on electronic voting systems, which is very well known that it's one of the hottest topics in this year especially. He has many papers, publications, keynote speaker, and invited talks in many different conferences and journals. His work is very well recognizable in the academia and in this industry, and he's also a very good friend of mine, and I had the pleasure of talking to you and chatting with you with him in many different occasions. So David, very happy to have you as our keynote speaker, and we are looking forward to your talk.
Thank you. Thank you for that lovely introduction. So good morning, everyone. It's wonderful to see so many folks here. I'm sorry we can't be together in person. It'd be great to see all of you. I'm from the Bay Area, where we've got smoke from wildfires around. So every time I step outside, so if you'd like to have that experience, you could walk into your kitchen, find a match and light it and hold it under your nose for a couple of minutes. Or not. What I thought I'd do this morning would be try to highlight a few research challenges for the field. So if there are any grad students here who are looking for problems that might be fun to work on, looking for ideas, I hope that this talk will highlight a few. And as I'm talking, I also want to invite you to use chat. I know we're all distant, so maybe we can use this to form a little bit more of a group discussion. I invite you to throw in questions or argue with me or make fun of my slides or ignore me and interact with the other conference participants. So I love and I welcome heckling and interaction and you know, anything that comes to mind through the talk. I won't be offended. Okay, so let's start with using machine learning to detect attacks. And then I'll come back later in the talk to what vulnerabilities that might open us up to. Well, we could see in the literature 3 common techniques to trying to detect attacks in whatever domain we might be looking at. Maybe it's network intrusion detection, maybe it's spam detection, maybe it's some other kind of malicious activity. Probably the most widely used method in industry is to use signatures, the rules for detecting known bad behavior. Another approach could be to use a supervised learning, a machine learning classifier to try to learn which kind of events are malicious and which kind of events are benign, and then classify future events to detect attacks. And then a third broad approach is to use anomaly detection. Look for events that are unusual, they're anomalous among benign data. And if you see anything that's sufficiently anomalous, enough of an outlier for the benign data, then you might suspect that you're under attack. Okay, so if we just kind of look at the pluses and minuses of each of these approaches, well, signatures are a very natural approach that can be adopted fairly readily. From an engineering perspective, they've got a lot of attractive aspects. They can be labor intensive to craft the signatures. It requires expert analysts to write a signature for each type of malicious behavior that you're trying to detect. And they can be ineffective for new or novel attacks. They only detect known stuff. So that motivates us to look at classification and anomaly detection. And classification, the promise of that is if maybe we could have a classifier that learns to detect signs of malicious behavior, and so therefore reduces the workload on analysts and can detect new attacks. But one of the big challenges with that is the base rate problem. And in particular, imbalanced training set. That it's very common that we can find a training set with millions and millions of samples of benign stuff, but it may be challenging to find many examples of known attacks. If you want to detect intrusions on your corporate network and you've had 3 intrusions over the past year, you might have millions and millions of examples of benign data, but only 3 examples of malicious data. Now, if you try to train a classifier on a training set that has 1 million benign samples and 3 malicious samples, then you have a severe problem with class imbalance, and many classifiers don't work well in that setting. Finally, anomaly detection has the benefit that you don't need any samples of malicious behavior. Anomaly detection works by characterizing benign behavior. You take lots of data about benign behavior and detect what's normal among benign behavior. But seems to have had very little adoption in practice. And one of the reasons is it's very fragile. It tends to have a very high false positive rate because of what I'll call benign anomalies. Events that are anomalous, they're unusual among historically benign data. They're truly an outlier, but they're not an attack. There's some other explanation for why this is unusual data. So let's look at how we might deal with these issues. Well, I'm going to focus in on anomaly detection because there's been so much research on it. It looks so promising, and yet it's does not seem to have had the impact that's proportional to the amount of research work that's been done on it. So in traditional work on anomaly detection, the setup is something like this. We have for each event, we have a feature vector X, and then we get a distribution on the benign events. Okay, so we imagine some source of benign events that induces a distribution on these samples X. And I'm going to write that with as P of X given B, given that it's coming from a benign source. You could also have a malicious source of data as well. And in anomaly detection, the detection rule, the detector works by computing the likelihood of the data under a benign source. And when you see a new event, you check how likely would that be to occur among benign stream of events. And if it's sufficiently unlikely to occur among benign events, if that probability is below a threshold, then you raise an alert. You say, whoa, this is too weird for me. It's unlikely this would come from benign data. So therefore, I infer it must be malicious. And there's all sorts of techniques for how you instantiate this by constructing a statistical model to compute that likelihood, P of X, from the benign data. So the basic approach is we gather lots of historical data that we just assume to be benign. You train a model that lets you estimate these probabilities, and then you use that at test time to generate alerts and detect attacks. Problem solved? Are we done? Can we go home? Well, sadly, no. So here, let's check and see how you're with me. For those of you who've worked on anomaly detection, where does this fall short? What are the shortcomings of this approach to detecting attacks? You want to type in the chat and share what your thoughts are? It'd be hard to get a baseline of benign data. This historical data could contain malicious events in it, and then that would mess up our model of benign data. The false positives, yeah, false positives are a huge problem. When you actually do this in practice, you find that data activity there's an enormous amount of diversity, and that causes too many alerts, too many false positives. And one of the reasons that happens, folks are diving into some of the reasons here. That's great to see. Yeah. One reason is distribution shift. The distribution of on the benign data can change over time. And then your historical model is not the right model for the future. So I'll come back to that one. Base rate, yep. We, in practice, might need a false alarm rate that's below 1 in 10 to the 6th for this to be practical. So you have to get a really low false positive rate. There's a gap between attacks and anomalies. Absolutely, yeah. Just because something anomalous doesn't mean it's an attack. It might be a misconfiguration that causes behavior to look weird. It can be hard to determine the threshold. Yeah, that's kind of an arbitrary setting. There's some parameter tuning that's needed. Alerts may not be actionable. It's hard to know how analysts to interpret it. You have a black box system that says, this looks dodgy, but I can't tell you why. Who curates the verdicts? Yeah, it can be a lot of work for an analyst if the system's raising a lot of alerts to have an analyst look at each one of these. Okay, that's great. That's great. So let's compare what you came up with to what I hit on my slides. You had a much better list than I did. So one that I really wanted to focus in on is problem of false positives, which come about because not all anomalies are actually attacks. And in some of the work that our group's done, we've seen three things. First is distribution shift. The distribution of events changes over time. I get a new laptop, and now the events that I'm generating look different. They have a different IP address because I have a new laptop. Maybe there's a new operating system, so there's different kinds of traffic that's coming out of my laptop than my old laptop. Second, there's a long tail. There's an enormous amount of diversity. If you want to model this very accurately, you may need a lot of historical data to be able to accurately model these rare events that are fairly rare, but do happen. Third that I want to talk about is that anomaly detection has no notion of what kind of events should raise your suspicion of an attack. Like which ones have an indication or a sign of malicious behavior, as opposed to something else that's unusual but not malicious, like configuration error or some change in the underlying process. Okay, and that's kind of obvious in retrospect when you look at how the anomaly detector is trained on only benign data, historical benign data, but it's not trained on any malicious data. So it has no conception of which aspects of an event might make an analyst look at that and say, whoa, that really looks like something an attacker might do. Okay, so let's dive into each one of these. And I want to start by diving into the third one and look at a little bit of theory that's going to help us understand this, or give one way of thinking about this that I find helpful. Remember the setup. We've got an event is represented by a feature vector X. Every event comes from either a benign source or it comes from a source of malicious data. So that gives us two data distributions here. The conditional distribution on X given that it was benign, the conditional distribution on X given that it was malicious. And then what we want to do is a statistical inference task. We observe X and we want to infer whether it came from the benign source or the malicious source. And the optimal decision rule is to look at the conditional probability. The conditional probability this is benign, given that we observe the feature vector X. And if that probability is below some threshold, then you should raise an alert. And how you set that threshold depends on the costs of false positive versus false negatives and other factors. So let me just set aside how you set the threshold. So statistical theory tells us that's the optimal decision rule. And for various reasons, it's often useful to work with, instead of probabilities, to work with odds ratios. So I'm going to suggest we look at the ratio of the probabilities. The probability that this is benign, given the observed X, divided by the probability this is malicious, given the observed X. You can convert between the probability and this ratio in a straightforward way. So the Neiman-Pearson lemma, if you're familiar with that for hypothesis testing, tells us that the optimal decision rule for deciding whether to raise an alert, whether this event is should be treated as benign or malicious, is to look at that ratio. And if it's below some threshold, then you raise an alert, treat it as malicious. Okay. So the problem reduces to being able to compute these conditional probabilities, the probability that is benign given that you observe the feature vector X, or the probability it's malicious given you observe the feature vector X. So how do we compute those probabilities? Well, statistical theory says you can use Bayes' rule. Okay. So that ratio can be obtained by doing a Bayes update. You start on the prior, which is this ratio that's the prevalence, how often are benign events compared to how often do malicious events happen. So that ratio might say benign events occur 1 million times as often as malicious events. And then you update your prior based on the evidence, based on the observation of the feature vector X. You see this event X, and now you want to classify that event as either benign or malicious. So that event X gives you some information about whether this came from the benign source of data or the malicious source. And the information is given by this likelihood ratio. You compute the likelihood of X occurring among benign data, the likelihood that X would occur among malicious data, take that ratio, and that's how you update the prior. You update the prior by multiplying by the likelihood ratio. Okay, so that's what Bayes' rule says. So if we plug that into our decision rule for when to raise an alert, this theory tells us that what we should do, the optimal rule, is to raise an alert if the likelihood ratio is below some threshold. Okay. So I just want to highlight this as kind of the conclusion of this reasoning. We have some principled reason to believe the optimal decision rule would be, if we knew how to compute these likelihoods, to compute the likelihood ratio for the event we observe and check if it's below a threshold. Now let's compare. Let's go back to what anomaly detection does and compare. Traditional anomaly detection decision rule is to alert if the likelihood among benign data is below some threshold. And we ignore the likelihood among malicious data. But this reasoning just tells us that the optimal rule would be to look at the ratio of those two likelihoods and alert if that's below a threshold. So traditional anomaly detection is not using the statistically optimal rule. And so that's how we get to this problem that anomaly detection may raise alerts for things that are rare but don't look like an attack. because it has no conception of what looks like an attack. It has no notion of what the distribution, the likelihood of X, given they came from malicious data, has no way to model that. Okay, so this is a shortcoming of traditional anomaly detection. And now I want to suggest maybe a first research challenge for if there are any grad students in the audience looking for problems. Look for a way to incorporate, to improve anomaly detection by somehow including some notion of how much this event should make you suspicious that it's an attack versus some other kind of anomaly. Okay, if we could think of some way to model how much this event resembles malicious behavior. And you could formulate this as, how do we estimate this likelihood, the likelihood it comes from an attack, with very little training data? You might have millions of known benign samples to form a model for the distribution on benign data, but you might have very few malicious samples, so it's hard to get a good estimate of that distribution on malicious data. So is there some way that we could use, for instance, analyst expert domain knowledge, or some structure, or some assumptions that would help us model that with very little data? I don't know how to do that, so I'll throw that out as a research challenge for you. I'm hoping maybe one of the folks here will come up with some great ideas to solve it for us. Okay, so this is a lot of theory. Let me try to highlight or illustrate what I've been talking about now with an example and some pictures. So here's an example taken from some of the work in our group where we're trying to classify remote logins to detect which remote logins were malicious. And there's all sorts of features you could use to look at a remote login and try to get some sense of whether it might be malicious or benign. One example of a feature that seems to be very useful is you look at the IP address this login is coming from. You look at the past history of all the logins this user has made, what IP addresses they've logged in from, and you look at how common this IP address is among the historical data of the past year, let's say. Okay, so count how many previous logins this user has made from that same IP address and use that count as a feature. And then every login can be associated with that count. When the user logs in from a machine they've used a lot in the past, then that count will be large, that feature will be large. And when they log in from a machine that they've never used before, that count will be 0, it'll be very small. So that might give you some information about whether this is benign or if it's malicious. Probably often attackers log in from a new machine that the user's never used before. So then we can gather benign data, compute the feature values for the benign data, and get some distribution on the values of this feature. And maybe the distribution looks something like this picture here. Okay. So now, how are we going to use this for detecting attacks? Well, traditional anomaly detection would say that when you see a new login, you compute the value of the feature, and then you find where that falls on the x-axis. Maybe this is a machine that's been logged into 10 times before in the past year, logged in from 10 times. And then you go up on vertically among that point on the x-axis to find this frequency score among the historical benign samples. Okay, so in this case, we would see, oh yeah, that's in the middle of this distribution. It's pretty common to have a login where this feature value is 10. And so your detector, if you're using anomaly detection, would say not anomalous, pretty typical value of the feature, don't raise an alert, which seems like a sensible decision. That's what we would hope it would make. If the user's logged in 10 times from this IP address before, maybe we have no real reason to think that's an attack. That's just typical behavior. On the other hand, if we had a login from a new machine that had never been seen before, then the value of this feature might be 0. And then we look that up in the frequency score in this distribution, and we find that's very, very rare for users to log in from a new machine. And so then our anomaly detector would say, whoa, this is an unusual event. It's not common to see this, so raise an alert. Okay, and that seems pretty sensible. So far, this is in accordance with our intuition. that logins from a new machine, it makes sense that those might be the most suspicious, that there could be an attacker attacking us. But there's a problem. I want to talk about a third case. Imagine we see a login event and the value of the feature is now like 100. So this is a machine that this user has logged in from 100 times before. And you might look up on that distribution and say that's way out on the right tail of the distribution. It's rare to see logins that have such a large number, 100. Well, then what's going to happen with the anomaly detector? The anomaly detector is going to look at that frequency score, say that frequency is very rare. It's very rare to see an event with a count with a feature value as large as 100. So the anomaly detector will raise an alert. And then we're sad because as humans with some knowledge of the meaning of this feature, we can tell that if the user's logged in 100 times before from this IP address, this is probably not an attack. It's probably them logging in from some machine they've used a lot before. Even though the feature value is unusually large, large numbers don't tend to make you suspicious of an attack. Only small values should make you suspicious of an attack. Okay, so this would be an example of shortcomings of anomaly detection because it has no notion of what looks like an attack and what looks like what doesn't. So in our work, we've looked at one candidate solution. This is work by Grant Ho and collaborators. He proposed a scheme called DAS. And what DAS does is kind of a simple idea. It says, well, we don't know how to model exactly what the distribution of this feature is for malicious logins because we don't have many known malicious logins to train on. But we can say that it monotonically decreases. The lower that feature, the more suspicious. The higher the feature, the less likely this would be seen in attack data. Attackers are usually logging in from new machines that users never used before. Okay, if you then make that assumption, then there's a natural thing to do, which is instead of using the point probability of seeing this feature value X among benign data, you use a tail probability. You say, what's the likelihood that among benign data we would see something with the feature value not exactly 10, but 10 or lower, 10 or anything more suspicious. Okay, and then now the picture looks. If you do this technique on our data set, we're looking at detecting spear phishing attacks, which are very rare. We found something like a 9-fold reduction in false positives compared to other methods for anomaly detection that don't have any notion of what malicious data looks like. So this simple assumption got you a big improvement. And if we kind of look through this example, the way that would work is when you saw this login that had a feature value of 10, we would compute the left tail. The left-hand side, all the events on the left-hand side are feature values that would be at least as suspicious of that or even more indicative of an attack. And then you would sum up the tail probability among the benign distribution. In this case, you might get an answer like a third. So it's not that unusual to see an event that's this suspicious or even more so. And so a detector would not raise an alert. DAS would not raise an alert on that. If you saw an event that had this feature value of 0, then the tail probability is very small. And if you saw, and it would raise an alert, and DAS would raise an alert. And if you saw a feature value is very large, like 100, then we would compute the tail probability, and the tail probability is very large. It's close to 1. Essentially, all of the mass is more suspicious than that. And so then we would not raise an alert because that's very typical from the perspective of suspiciousness. Okay, so now DAS, we're happier because DAS raised an alert for anomalies that are on the left side, the side that we associate with attacks, but DAS does not raise an alert for anomalies that are on the right side, the side that's not associated with attacks. So it has some notion of this directionality or where attacks are expected to congregate. So yeah, this is exactly using the CDF rather than the PDF, totally. And then if you read our paper, you'll see how we generalize this to multi-dimensional feature vectors. Great, okay. So that's the problem of modeling malicious behavior. Maybe you all can find a better solution for that. Another problem that you all raised was a distribution shift. So let's say we have our historical data from the past year of these feature values, and then coronavirus hits and everyone has to work from home. And now the distribution on feature values changes. Everyone's working from home from a new machine that they haven't logged in from many times before. And now this feature value is much lower immediately after coronavirus hits. Well, we have no idea that because we can't see that in historical data. Our historical data is that dark line, but the true distribution is this dotted line that's very different. So that's bad. That's bad for anomaly detection, because now if you have a feature value that's like kind of low, like over here, like 2 or 3, then in our historical data, that's very rare, and our detector will raise an alert. But we're sad because among the new distribution, that's actually a very typical value, and it's not, so we shouldn't be raising an alert. So this is very challenging to deal with, and I want to raise this as a research challenge for all of you here, is to think about how can we detect distribution shift, how can we manage the problem of distribution shift. It's a big problem. I've been talking a lot. Let me check in with you all and see, how are we doing? Any reactions, discussion, thoughts so far? Industry folks, what would it take for you to consider using anomaly detection? What do you see as the research challenges that academia needs to solve?
Just very quickly, David, there is one question in the chat window from Ben. And also I have a question. so
Love to hear your question.
Yeah, so is the is the kind of a directional monotonic property always hold? Are there cases where you have, somewhere in the middle of the distribution is considered okay, but both sides considered malicious?
Definitely, yeah. This monotonic thing was a fairly simple case that when we were looking at the features we happen to have for spear phishing, it happened to make sense. There's no reason to believe that'll be sensible for every feature or that things will be that simple. So I think it would make sense to look for methods that can be a little more sophisticated about the structure of what attacks look like. Yeah. I don't know how to do that.
Yeah, I was thinking, so far it seems that it's all relies on domain, expertise to identify what the meaning of the feature and how do you decide what direction of the feature is malicious. Things might get more complicated if features need to be combined to determine the semantic meaning of them. So it might be more difficult to do manually.
That's right. So I think one question that we could think about would be, how could we extract that knowledge that's in an analyst's head, that domain knowledge, in some relatively few number of interactions with the analyst that would help us form a reasonable model there.
That's interesting.
All right, I invite you all to jump in the chat or otherwise, and if you have thoughts, otherwise I'll keep going. Yeah, if we think of this as the training data is changing from an old distribution, an old training set to a new set, is there some kind of way we could measure the rate of change? That's a great question. I would love to hear your thoughts on how to do that. I would love to see papers on how to do that. I've listed a few papers that I really like in the lower right here. One of these was using a technique called conformal prediction to try to measure when you might be experiencing distribution shift. But I think there might be room for a lot more work here. One thing you can see from this discussion is that anomaly detection relies very heavily on constructing good probability models, good ways to estimate the likelihood or the probability of an event from occurring among benign data. And to learn that, from a training set of benign events. And so I'll just throw up a few techniques that I think are worth being aware of if you're new to this area. There's a whole bunch of techniques in the machine learning literature for generative models that could be used for this. It's a little bit different from classifiers that we're used to because we need not just a decision, yay or nay, but we actually need a probability score. So there are techniques, classical techniques, KDE, Gaussian mixture models, nearest neighbor, that work well in low dimension, but struggle to deal with high dimensional feature vectors. And then more recently, there's a bunch of work in the neural network space on using variational autoencoders, normalizing flows, GANs, and for time series data, LSTMs and autoregressive models that I think if you're working in this area, you ought to know about. There's some very beautiful techniques there. Indeed, this is totally the concept drift challenge. This distribution shift is the concept drift problem from the ML community. And what are the techniques we can steal from the ML community? I think that's a great question. Okay, so one challenge, research challenge that I think would be useful is if you wanted to work on a point problem, building better probability models for modeling this probability, estimating this likelihood score for complicated domains like network traffic, network events, remote logins, or log entries from syslog. And it's fairly challenging to figure out how to deal with this. We could look at a single event in isolation and model its probability, but really we ought to think of that event in the context of events that have preceded it. Like when a user logs into a machine, then that changes the distribution on what events you should expect to see occur from that machine. And so capturing that dependence now is a lot more challenging. And I think there's room here for papers that don't build an entire detector. They just give us a piece of technology, which is build me a better probability model for benign data. I think another interesting research challenge that in the research world goes underestimated, but I think is very important for deployment, is data cleaning and data gathering. The problem starts not with clean data, but we've got messy sources of data from log entries that we have to then turn into these features. And in our work with a corporate partner, what we've been observing is there are a lot of challenges in this. For instance, one key challenge is to figure out how to obtain persistent host identity for hosts if you're looking at network traffic, because due to DHCP, remote access, VPNs, one machine can have multiple different IP addresses. And if you want to assign some profile to a machine or track events of that machine over time, you need a way to map those to a persistent host identifier. And I think there's some good work to be done on how to do that and how to maintain a mapping between a host name and different kinds of identity. Another challenge that I wanted to highlight for you is one that might not sound like a security challenge, but is I think a useful building block for building better detectors. And what we've noticed is that it can be very useful to be able to assign some attributes to a machine. Like, is this machine a client? Is it like a person's laptop? Or is it a server? It's like something sitting that people connect to. What user owns it if it's a laptop? Who owns it? Whose personal machine is this? What operating system is it running? So figuring out how to infer that. If you're lucky, maybe there's a database in the enterprise where you can look that up, but there might not be. And then can we infer that from network traffic? So I think there's a great opportunity from some papers that look at network activity and then infer this kind of information. Another kind of attribute that'd be very useful for detection is users, characterizing users in an enterprise. Who are the sysadmins? What are the groups? You know, what's the group of developers? What's the marketing group? What's the communication patterns between users? What's the hierarchy for a given user? Who's their boss? Being able to infer that from observations that are readily available, the logs that are readily available, like network traffic or system logs, would be a useful building block that I think would help us build better detectors. For those of you who are interested in working in this area, I thought I'd just throw up a few data sets that I think are interesting. One of the biggest challenges in working in this problem is getting realistic data. For industry folks, one way you can contribute is by partnering with academics if you have data that you'd share. And for academics who aren't lucky enough to have that kind of corporate partnership, I'll throw up some data sets that might be interesting for you to look at, and you can look at my slides and look up these later. All right, I saw in the chat someone suggested distributional regression used to model distribution, concept shift, changes in the distribution. Oh, cool. Okay. I didn't know about that. Thank you. I think one more challenge to look at for anomaly detection might be triage. When you have an ML model, there's a classifier or anomaly detector. Might want to surface that to an analyst. How do we help an analyst to quickly verify whether or not that is indeed an attack or not? It can be very time consuming. The ML can be like a black box that gives the analyst no clue why this alert was surfaced. So can we do anything to help the triage process run faster? And in work we were doing on detecting spear phishing attacks, we discovered something interesting, which was that analysts, working with analysts, discovered that 98% of the false positives from our anomaly detection method could be ruled out in 30 seconds per alert if we presented just 3 top attributes of each of the suspicious email: the subject line, the from line, and the URL in the email. And then only 2% of them, the analysts need to dive into more detail, looking at network traffic logs and what did the user do after they read that email and so on and so forth. So that's a fairly simple case where it was the same 3 attributes that should always be presented to the analyst. Is there something more sophisticated we could do, and can we generalize to other tasks? For instance, learning which features to show to analysts first, to look at first, or providing an explanation of why the ML model made this decision, or which aspect it's unsure about and will be most profitable for analysts to look at. So I think there's a great research area.
Quick question,
all right,
David.
Moving on.
Sorry.
Yeah.
So I'm just wondering if analysts would take several seconds to determine if this is a true alert or not. What prevent machines and algorithms to do the same thing?
Yeah. What were analysts doing that the machine couldn't? In the spear phishing example, they were looking at like the text of the subject line, and they were using their domain knowledge about what lures phishing attacks tend to use to look at, does that subject line sound like the kind of thing that a phishing attacker might use? And then they would look at the URL and they would say, does that look like, that might plausibly be benign given the subject line or not? So there was some human knowledge in there about like natural language that was not easy to model in an ML model. So I don't know what the general answer is, but that's an example from this one specific case.
From my experience, sometimes people will even take like half an hour or 1 hour to review the detection results because I'm working for the network security, especially for DDoS detection. The mitigation results or detection results will affect like thousands of users in the network. So it is a very serious problem. Yeah.
Does anyone else have any experience about this triage, this aspect?
I had just one other question about it. For the 3 that you found, the subject, from and URL, was that found by an ML model to be like the most important attributes, or those just from the analyst's feedback?
That was the analyst's feedback. So we had no systematic way to learn that, and it was very specific to this one scenario. And so I would love to know how you would approach that for a new task.
Well, interesting.
Just a quick side note. I'm surprised that the from field is actually one of the attributes, since considering that spoofing is entirely feasible in many of the spear phishing attacks. So
that's a good point.
Yeah, what kind of analysis take from there? Is the from always trusted?
I'm not sure how the analysts were using the from. I think that one of the threat models on their mind was BEC attacks, where it's spoofing the identity of someone trusted. So I'm speculating now, but it's possible they might have been looking at the from to say, did it look like this is trying to spoof the identity of someone trusted within the enterprise, like a CFO or something like that? But that's just speculation. I don't know.
I see.
So just sharing my experience, I had the pleasure of working with some of these great analysts, And at the beginning, I was trying to sit behind their, desk and look at them how they do it. The challenge here is that, they step by step move on and reduce the search space that they have. So they see this from, and then they do another search from somewhere else and then connect it to the URL and then look at this, look at that. So as David mentioned, I believe that the model is a little complex for us to actually model it in the ML, and we don't have the data that covers all the activities that they do, given the complexity of the work that they do, given based on their experience. And I think that's one of the challenges for us as researchers, to be able to find the systematic way to model that, because it's a very challenging task and very complex task that they do in order to, yes, they do it in 30 seconds, but they rely on years and years of experience to do that in 30 seconds.
Well said. All right. Let me move on to signatures. Signatures are so widely used in industry. I think that as a research community, we ought to be looking at how to make signature-based systems more effective too. So, for instance, you might have some pipeline that's analyzing a Windows executable to try to detect if it's malicious, and it might have a signature to detect the Petya attack, and another signature for WannaCry, another signature for CryptoLocker, another signature for Mirai, maybe some signatures for benign, common benign examples. You might have a whole pipeline of signatures that capture different kinds of known malware families, known malicious behavior, and so on. How can we help companies improve those kinds of detectors? I think that's an interesting question. One of the commonly cited shortcomings of the signature-based detection is the risk of evasion. That attackers may be able to make a minor change to their malware, and it no longer matches the signature and won't be detected anymore. So signatures can be brittle against evasion. And I think it'd be interesting to think a little bit about how whether evasion could be addressed through dynamic moving target techniques. How we could dynamically adapt signatures, and when should you change or update the signature. So let me try to give one kind of candidate game theoretic perspective. I don't want you to take this too seriously, but just to try to give you some example for maybe how we could study this. We could imagine making some assumptions from some economic model, like it costs a certain amount to construct a new signature. We can task an analyst to go write a signature for a malware family. Maybe it takes them a day. So maybe think of it as costing, let's say, $1,000. You can make a new signature for the family anytime you want. You can have them, make a new signature make multiple signatures that are each looking at different aspects or different features, cover different pieces of the malware family. And meanwhile, what the attackers might be doing is they might be trying to evade detection so that your antivirus doesn't detect them. And let's say that the signatures are used in. Oh, go ahead. Did you want to comment?
I just want to say a comment that if you guys don't have a question, please mute your machines.
All right, so what we see in practice is that attackers will often try to evade detection. And typically, how do they do that? They're just making small changes to their malware, and then running against this cloud detector to see if it's detected, and hoping that they stumble across some change that will invalidate the signature and escape detection. Makes sense. So let's just make up some numbers. Imagine they're going to try 100 of them per month. This is just kind of the rate of change that they go through, and they'll keep trying until they find one that works. And when they find one that works, then they'll start using that. And let's say that each change they make has some probability P of evading the signature, and then there's some cost to us as defenders if the attackers evade, because there's some time period when that malware family is no longer detected, and users get harmed. And it takes us a while to respond and notice that and make a new signature. And in the meantime, our users have been harmed by this malware. Okay, so then we need to put some cost on that. And I don't know how we assign a cost to that. So there's an economic model. We could now try to use some game theory to try to analyze what's the optimal strategy for when to construct new signatures. One plausible strategy, for instance, would be anytime you detect that your signature is no longer working, you notice that you're not detecting that malware family anymore with the signature you got, then you task an analyst to write a new signature. That's a plausible strategy. So write signature, a signature only when needed. Another plausible strategy would be to say, let's write multiple signatures up front, multiple independent signatures. I'm going to have the analyst spend 3 days crafting 3 totally different signatures, and raise an alert if any of those fire, with the hope being that's going to cost me 3 times as much, but the hope is going to be a lot harder to evade, because now an attacker who has an evasion, it has to simultaneously evade all 3 of those. And that's a much lower probability that the evasion simultaneously evades all 3 signatures. And if it doesn't evade all 3 signatures, then the attacker's gotten nowhere. So then we could try to, form a model of the expected payoff for each of these strategies, figure out what's the optimal one. I suspect we might discover that there might be some cases where we're constructing multiple signatures is actually better, that rather than writing a new signature every time the attacker evades, that's sort of like having a series of fences where each fence is a little bit higher than the previous one, and you're teaching the attacker how to jump better, that maybe it's better to put all your money into having one really tall wall so the attacker kind of never really, makes any progress. But I don't know. And maybe you can find a better model for thinking about when should we change signatures? When should we write new signatures? How do we do that? How do we tell when a signature is no longer working? All right. Let me pause here for comments, questions. I think I want to shift at this point to talking about adversarial examples and attacks on malware and the vulnerabilities, attacks on machine learning and the vulnerabilities that it introduces if we use machine learning to make security decisions. But before I do, I just want to take a moment to pause. Any discussion here? Comments?
But before we move on from the anomaly detection, one question they have is that most of the times when we are talking about anomaly detection, because we have a meaning of anomaly as human analysts, all the features, all the parameters that we define for the machines are human understandable features, because otherwise we cannot even define anomaly. One of the advantages that we have in some of the machine learning technology, especially in deep learning technology, is that we avoid the need for feature engineering. We just let the model consume the raw data. How can we bridge this gap in anomaly detection?
I got another suggestion privately that it'd be interesting to look at human in the loop to learn from analysts' previous decisions. So some kind of active learning where we look at the alerts that were presented to analysts in the past and what decision they made. Maybe they tell us what decision they made, maybe they didn't tell us why. And then can we use some technique to learn from that so that for future alerts, we can predict what an analyst would do. Maybe some kind of clustering or some other learning method. Yeah, I think that's interesting. All right, let me move on to attacks on machine learning. I want to talk about the problem of adversarial examples. I'm curious, how many of you are already familiar with adversarial examples? Would you go into the participants thing, the participants bar, and leave me I don't know if you can react there. Maybe you can't. Well, leave me a note in chat. How many of you are familiar with adversarial examples? Give me a yes or no if you don't mind. All right, lots of yeses. So then I can fly through this. I think adversarial examples pose a challenge for us anytime we're using machine learning to make security decisions, like whether to raise an alert or not. And they've been very well studied in the space of images. For instance, for image classifiers that take an image and classify what kind of object is there. On the left, there's an image that is classified as a school bus, and it is indeed a school bus, as you can see. And on the right is an image, it looks identical to you, but it's actually not. Changes have been made. The changes are so small, you can't see it with your eyes. but they were chosen in a very deliberate way to fool that particular classifier. And they fool the classifier into thinking that's a hummingbird. And you could fool the classifier into thinking it's anything you want. You could make it think it's an ostrich, it's a tank, it's a skyscraper, anything you want. So our machine learning models are very fragile to attack, to deliberate modifications to the image. So these things are called adversarial examples, and they seem to be a very fundamental feature of our current machine learning methods, especially neural nets. And the issue, the scary part, is that then attackers might be able to use them to modify the data so that the machine learning model makes the wrong decision and doesn't detect an attack. So our detector makes the wrong decision. And in the computer vision space, this is very well studied. There's a lot of work, and I thought I'd highlight a few for you because I think it's kind of fun. So for instance, here's work with LiDAR sensors for autonomous vehicles, self-driving cars. This is a paper that I enjoyed that crafted an adversarial object. That object on the white as a particularly crafted shape that was crafted to fool a LiDAR-based classifier. You stick that in the road, as shown in the image on the left, and that'd be an obstruction you don't want to drive over, but it's invisible to this state-of-the-art LiDAR classifier. The classifier doesn't see anything there because that shape just confuses it so much. Or in autonomous vehicles, a lot of people talk about autonomous vehicles as a motivating example because there's use of machine learning to make decisions that are life critical, safety critical potentially. So here's another paper that I enjoyed that took a ML model for steering a car. It takes the camera view and predicts whether you should steer left or straight or right, and works pretty well, except when it's under attack. So on the left is an ordinary clean image taken from everyday driving, and you feed that image to the classifier, and it steers the car to the right, which is good because the road is curving to the right, so all good. You take the right image has been maliciously modified, crafted in a way to fool this ML model, and you probably can't perceive it, but this is taken from the paper. It was constructed, and now the ML model steers to the left right into that incoming traffic. Not good. Okay. So demonstrated in the lab, not out in practice. They're modifying each individual pixel by pixel, assuming full control over that image. But if you have that kind of control, then you can just send the classifier way astray. And here's another example of folks who said, well, we can do this not just in theory, but actually we could come up with a way to make a malicious patch on the road. This kind of rubber mat that has something printed on it that's it looks like noise to our eyes, but is deliberately crafted to fool classifiers. And they show that this is actually fairly robustly fools the classifier as you're driving along. The ordinary image, the classifier detects you should go straight, but when there's this thing on the road that was put there by an attacker, now it tries to veer off into the oncoming traffic. And this is not just theoretical in the lab stuff. Here's a paper from last year that looked at the Tesla lane keeping system, and they found that if they painted 3 white dots in the road, you could just barely see them, but inside those red circles, there's a white dot painted in the road. Then this car will drive down the road, stay in the lane, and then it'll suddenly jerk to the left into the opposing lane because it thought those 3 dots were enough to make it think there was a lane markers just in the road curve to the left. So a very simple kind of adversarial example. And so the takeaway that I'm trying to get at here is we know that this problem exists really bad in the vision domain. And everything we've studied, every domain we've studied, we see analogs of this problem as well. So the lesson seems to be that any system that uses neural networks to make decisions is potentially susceptible to attack. And that's scary because I was just talking about using neural networks for classification or anomaly detection to detect what are attacks, to raise an alert if we see an attack. And yikes, what this should make us worry about now is that an attacker can modify their network packet or modify their malicious, their malware program a little bit to change a couple of the feature values a little bit, and that there will be very small changes that will suffice to fool the neural network classifier. And unfortunately, we know of no good defense against this problem. It's been intensely studied over the past 5 years. There's over 2,000 papers now that have been published on the problem of adversarial examples, and we have no defense that's very satisfactory. So I'll talk you through the 3 leading defenses, but with the caveat that while they make it harder to find adversarial examples still exist. So they're not really an answer yet. The first leading technique for hardening your classifier against this adversarial example problem is called adversarial training. And the analogy here is, think of like vaccination for immune system. When we give you a vaccine, we expose your immune system to a synthetic, like a little bit of the disease, a little bit of the germ, maybe a synthetically crafted one. And that teaches your immune system how to respond. So we're going to do the same thing with a machine learning model. We're going to, at training time, the defender will synthetically craft some of these adversarial examples, these attacks, and then add them to the training set and say, tell the model, try to teach the model to produce the right answer on those attack images or attack samples. That's adversarial training. You repeat that until convergence, and it helps some, but not enough. The second leading technique is one that's not very well known among most people, but I think deserves to be better known. It's using generative models, variational autoencoders, for instance, to compute a clash conditional likelihood for each class, and then estimating the class conditional likelihood for each class, and then classifying by choosing the class that has the highest likelihood. And it turns out if you do that right, there's some work from Lucas Schott et al. That shows that for some tasks, this can give significantly better robustness against adversarial examples, even better than adversarial training. The downside is that our generative models are only able to handle relatively simple classification tasks. So for many tasks, this is not feasible. But there's a beautiful paper from Schott et al. On defending MNIST against adversarial examples using this technique that I think deserves to be better known. And then the third technique that is just starting to be explored in the past year or two is randomized smoothing. And in randomized smoothing, what we do is we noise up the feature vector before we feed it to the classifier. It's a very simple looking defense. You add some noise to the feature vector, you classify, you do that many times, and you take a majority vote. Sounds very simple, and it appears what it does is that it helps somewhat mitigates the issue of adversarial examples by making the machine learning classifier have a smoother decision boundary at the cost of taking a lot more time at test time to run through many noised up samples through the model. And there's a lot of literature on each of these. I'd love to talk to you more separately about how they work if you're interested. There's a lot you could learn about, but I just wanted to expose you to these 3 techniques. If you're interested, I could ask me about the generative model technique. I can talk you through a little bit how that works. In the interest of time, I'm going to skip past that. And I'm going to jump on to maybe some concluding remarks and research challenges for those of you interested in adversarial examples in the space of detecting attacks. I think all of our machine learning based detectors that are using ML to detect can probably be attacked with adversarial examples. And we don't have a whole lot of work on validating that, but we've seen some papers that have started to validate that. And so I think this is a threat that we don't see today, we won't see immediately, but eventually attackers will have an incentive to try to evade detection and may start using these attacks against us. We have no good defense right now, so I think it would behoove us to start thinking about proactively what could we do to defend ourselves against that kind of evasion attack. For instance, it may be hard to stop all adversarial examples, but can we come up with some limited threat models that we can defend against? Like maybe the attacker will take their malware and add a little bit of benign functionality to it in hopes that that makes it look benign. Well, can we at least stop that class of attacks? Also think it'd be interesting to explore how well do these standard defenses work for detectors in the security realm, like malware detection or spam detection. They've been studied a lot in the vision space, but not a lot of work looking at them in the space of security and attack detection. So for now, if you're in industry, the best answer I've got for you is to keep your models secret. Be prepared to change them if you start to come under attack. We don't see these attacks very much right now, but I don't have a good answer for you. And so I'll raise that as my last research challenge for the community, which is to find a way to make our ML models robust against adversarial examples, so we don't have this big vulnerability just waiting to be exploited in our systems. All right, that's all I got. Thank you very much for listening. I'd welcome your questions and discussion.
Thank you very much, David. Thank you very much for the great talk. Lots of really interesting information, and also thank you very much for masterfully keep us involved in this remote keynote session. It was really enjoyable. So we really appreciate it. I want to open the floor for everybody if they have any questions. If you want to type in the chat, I would, David would answer the questions. If you want to ask the question directly also, please ask the questions.
I'll start one. So traditionally, to understand some of the new attacks and how the attackers changes, we have something like a honeypots. We basically deploy them and capture new attacks we've never seen before and analyze them. I was wondering, have you thought about something similar from machine learning models, to catch adversarial attempts to evade the model? Would it be possible to deploy something like machine learning honeypots just to capture them, to analyze them?
Very interesting. To try to characterize and capture how are bad guys evading.
Right, just analyze the queries maybe, to say, this does not look like anything legitimate, like try to send a traffic to me and do some legitimate task, but try to figure out how their gradient change. I don't know if there's a interface that we can explore, like checking those kind of activities.
I think that'd be really interesting. In our group, we thought about doing something like that and then somehow ran out of energy or time. One source to look at might be VirusTotal. For some malware families, there's semi-reasonable, antivirus detectors do a semi-reasonable job of categorizing malware samples according to what family they're from. And then you can try to download over time samples that are observed from that family. And then you could try to measure what changes over time. What does the evolution look like? And what are attackers changing? It may be hard to know what's changes being done for reasons of evasion versus other reasons, but that might give one avenue to explore. Yeah. I also think it's an interesting problem to look at if attackers are trying to probe our classifier,
right,
to try to find how to evade it. Maybe they're repeatedly issuing queries until they find one that fools it. Can we detect that kind of activity?
Yeah, so essentially, instead of deal with adversarial machine learning directly, kind of put a box surrounding it and as guarding the interface.
Right. And one of my students done some preliminary work on that, where trying to detect the patterns that you might see among those probes. And what we noticed is that standard attacks that work by probing like that, many of them involve making very small changes to a sample. You take a sample and they make a small change, and you see how does that change the classification, make another small change, and what does that do to the classification, and repeat. And so then that introduces a pattern that's potentially detectable, that you see many, kind of a cluster of queries there. Each one is very similar to a previous one. And if you can somehow measure similarity, then you can have a hope of detecting that attack.
Yeah, that's interesting. It's interesting. More questions.
This is a great question for discussion. Maybe let me open this up to everyone. I'm not sure I have any special insights myself on advances in ML have been revolutionary for fields like computer vision and speech and NLP. but the impact on cybersecurity seems to be much slower. Any thoughts on why that is?
Could it be, this is Jonathan Hodap, calling from San Diego. Could it be that in cases like computer vision and speech and NLP, you're kind of talking about static sets, i.e. here's a bunch of text, or I'm going to run through all this speech, or even with the vision, I'm going to be driving around on a test track. Whereas in cybersecurity, you're up against an active adversary. I don't think we've tried to do computer vision on cars on road surfaces that are constantly changing. Whereas when you're up against the human brain and thousands of human brains, the problem set is no longer static. Just a thought, over.
This is Adam Hunt from Risk IQ. What we see is when we produce even a small number of false positives, our customers are very vocal about it. And so when our precision has to be in the 99.5 and higher rate, and that's very difficult to achieve without a lot of human in the loop intervention and a lot of highly tuned classifiers. And like you mentioned, keeping up with it is also very critical. So having a model that can pull things in using active learning, allowing us to feed back into the model, that's very critical. So it's hard to do. Yeah.
I wonder if data sets are an issue as well. Computer vision, there's lots of standard data sets that are huge and they're very helpful. And it's more challenging to get data in the security realm.
Also labeling, because usually for vision or speech, we have human oracle. So you look at an image and you know what it is most of the time. But in malware or cybersecurity things, even labeling things sometimes takes some efforts, resources, and having reliable labels also is a challenge to have in data sets.
I think one potential reason could be is that, and I mentioned this in the chat, any potential improvement in research related to machine learning is probably any successful attempt or to improve an existing technique might be tried to be capitalized upon right away, and therefore the sharing and collaborative ideas are not very not really welcomed in the field sometimes. This is more, speaking from the industry perspective.
All right. Once again, thank you very much. We are getting close to the time for our session. So David, once again, thank you very much for the wonderful keynote. We really appreciate it and we really enjoyed that. So, on behalf of everybody, we really, appreciate and thank you for your time, your efforts, and it was really great. Thank you very much. Thanks.
Thank you.
All right.